All right, today we are going to dive into a completely different way of thinking about, well, everything. It's a theory that asks us to consider that everything we see around us, from the tiniest particle all the way up to the biggest galaxy, might just be the result of a single, ridiculously simple rule.
So let's just jump right into the big, mind-bending question at the heart of all this, posed by physicist and computer scientist Stephen Wolfram. What if our entire universe isn't built on complicated math equations, but is actually running on something more like a piece of software, a single, simple program?
Okay, so if you're going to try and build a whole new theory of everything, right, from scratch, you can't just use the same old tools. First things first, you need a brand new way to model the world, a different kind of toolkit altogether.
And this really gets to the heart of the shift in thinking. For more than 300 years, science has pretty much relied on mathematical equations to explain how the world works. But Stephen Wolfram's big point is, well, math is fantastic for simple, predictable systems, but it really starts to struggle when you look at the messy, chaotic, complex stuff you see all over in nature. So what's his solution? Ditch the equations and use simple programs instead. And it turns out these simple little programs are unbelievably good at creating complexity out of nothing.
So this new way of thinking is what leads us to the core discovery. And what's so cool is that it didn't come from looking through a telescope or smashing atoms together in a particle accelerator. Nope, it came from exploring this huge, abstract universe that's made of nothing but pure computation.
The tools he used for this exploration, they're called cellular automata. Now that might sound complicated, but it's not. Just picture a single line of squares, or cells, like pixels on a screen. Each one can be either black or white. And the whole system just grows, one line at a time, based on a super simple rule that only cares about a cell's immediate neighbors.
And when I say simple, I mean really simple. Here's how it works. You look at a single cell and its two neighbors, one on the left, one on the right. That little group of three, there are only 8 possible ways they can be arranged. White, black, 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 and so on. The rule is just a little lookup table that says for each of those 8 patterns, what color the cell directly below it should be in the next step. That's literally it. You just do that over and over and over again for every cell.
So, with a setup that simple, how many possible programs or rules could there possibly be? Get this, just 256. That's it. It's an unbelievably small number. You could literally sit down and explore this entire universe of possible physics on your computer in a single afternoon.
And that's exactly what Wolfram did. And in the process, he stumbled upon something he personally calls his all-time favorite scientific discovery. See, most of those 256 rules did what you'd expect. They made simple, boring patterns, or they just repeated themselves forever. But a few of them did something else entirely.
And that brings us to the main event. Meet Rule 30. And just remember, this isn't some complex algorithm, it's just one of those 256 simple little lookup tables, defined by just a handful of bits.
But when you take that simple little rule and you just start it off with a single black cell at the top and let it run, you get this. Immense, unpredictable, unbelievable complexity. It looks totally random, right? But here's the crazy part. It's not. It's completely determined by that simple rule. And this is the big takeaway. The absolute key discovery. You don't need complicated ingredients to get a complicated result. Simple rules can, and often do, create massive complexity. It's just a basic fact about how computation works.
Okay, fine. So simple rules can make complex patterns. That's a cool computer science trick. But what does that have to do with our universe? Well, this is where it gets really wild. The idea is to take that exact same principle and scale it up. Instead of applying it to a simple line of cells, what if you applied it to a gigantic, sprawling, interconnected network? A network that could actually be the fabric of space itself? Now we're getting ambitious. We're talking about rewriting what we even mean by space and time.
We usually think of space as this smooth, continuous, empty backdrop. It's like a stage, and all the stuff in the universe, planets, stars, people, are the actors on that stage. Well, in this new picture, forget the stage. There is no stage. Space is the actor. It's this giant network made of a huge number of discrete points. You can think of them like atoms of space, all connected to each other. And everything, I mean everything in the universe, isn't in the network, it is a part of the network structure.
So if that's space, then what's time? Well, time is in some fourth dimension that we're moving through. In this model, time is the computation itself. It's the step-by-step process of that fundamental rule being applied again and again and again, constantly rewriting the connections in that giant network of space.
The ticking of the clock is the universe running its code.
Okay, so let's recap. We have this idea of a network of space that's constantly being updated by a simple rule. This is where the theory goes for the grand prize. The claim is that this one single idea might just be the thing that finally connects the two towering achievements of modern physics, Einstein's relativity and quantum mechanics.
First, let's talk about Einstein and general relativity. In this model, what we call energy is really just a measure of how much computational activity is happening in one part of the network. And where there's a lot of activity, a lot of rewriting going on, it actually causes the network itself to bunch up and curve. And guess what that large-scale curvature of the network is? It's gravity, plain and simple. It's not some mysterious force, it's just the shape of space-time.
But what about the weirdness of quantum mechanics? Well, the same basic idea works there too. See, at any given moment, there isn't just one way for the rule to update the network. There are many possible ways. The theory says the universe doesn't pick one, it explores all of them simultaneously. This creates this incredible branching web of all possible histories. And here's the truly amazing part. If you take that same idea of curvature, but you apply it to this abstract space of all possible paths, you get the fundamental equations of quantum mechanics. It just pops right out.
So what does this all mean? It means that general relativity and quantum mechanics, these two theories that scientists have been trying to smash together for 100 years without success, might not be two different things at all. They could be the exact same fundamental theory, born from the exact same computational rule. It's just that one describes the curvature of physical space, and the other describes the curvature of this space of possibilities. This all leads to some pretty deep, almost philosophical questions. If the universe really is just one big computation, what does that say about things like free will or predictability? What does it mean for our place in the grand scheme of things?
There's this concept that's absolutely central to all of this, called computational irreducibility. Think back to Rule 30. There is no mathematical shortcut, no clever trick to figure out what the pattern will look like a million lines down. The only way to find out is to actually run the program for a million steps. Now, what if our universe is like that? It would mean that there's no way to predict the future except to live through it, to let the universe run its own computation. The very passage of time might just be this irreducible process of the universe figuring out what happens next.
But wait, this creates a huge puzzle. If the source code for our universe is actually simple, well, that feels a little too special, doesn't it? It kind of goes against this core idea in science that we're not special, that we don't occupy some privileged place in the cosmos. I mean, out of all the zillions of possible rules the universe could have, why were we so lucky to get a simple one? And this is where we get to the final, most mind-blowing twist. Maybe there isn't one special rule. What if the true fundamental reality isn't our universe at all, but some vast computational space where all possible rules are being computed, all at once? If that's true, then our laws of physics, everything from gravity to quantum mechanics, aren't the laws. They're just the description, the language that creatures like us, with our particular brains and senses, are able to perceive. We're just looking at one slice of an infinitely complex reality. And it really makes you wonder, what other kinds of physics, what other kinds of universes are being computed right now just outside the bubble of our human perception?